Okay. So again, I mentioned this the other day, so I'm going to do it again.
Afternoon announcements. I just have a message in the office for Harlan Paul. And again, students, if you've not yet brought your report card envelope back, and if your parents would like a meeting with some teachers, we kind of need that today, as we don't have school boards, parent teacher reviews. Those announcements. Enjoy your afternoon.
All right, let's have a look at this question and go through the whole process, with the exception of the, we don't need to put the objective one in, that'll be in 6.4, but, okay, so to raise funds to buy new instruments, the band committee has 500 t-shirts to sell. The t-shirts come in red or blue. Based on sales of the same t-shirts at a fundraiser 5 years ago, the committee expects to sell at least twice as many blue t-shirts as red t-shirts. Define the variables and the restrictions. Okay, so first things first, X and Y's are defining. We need to establish what's X going to be and what's Y going to be. What is X here?
The red shirts.
Sure. Red. Therefore, Y is blue. Blue. Good. What are our restrictions on this guy? For both? Can't sell part of a shirt, correct? Good. Okay, so that's my restrictions. My restrictions are the whole number. So that now narrows down my graph to where? First quadrant. Very good. Okay, now we have to work with the constraints. How many t-shirts do they have total?
500.
500. So the number of red plus the number of blue has to be less than or equal to 500. There's my first constraint on that. When I add them together, the total has to be less than or equal to 500. Right? I don't have more than 500 shirts, but I can sell as many as 500 shirts. And I have to add all my red and my blue to get to there. Now, the second constraint says the committee expects to sell at least twice as many blue shirts as red shirts. So how do I show that in an inequality?
X plus 2y is less than 55%.
X plus 2y is okay. Anybody else? Anybody have any ideas? Just throw some ideas out here, please, so I know you're not sleeping. Let's start with that.
Does it matter what order you put them in or not really?
Nope. Doesn't.
So how would you show?
Not there. Go ahead.
How would you show like twice as many of them?
Right. That's where I'm at. Okay. So I've used the 500 part already. What I need to show is that next statement that says the committee expects to sell at least twice as many blues as reds. So how do I show that? Well, let's narrow this down a bit. Somebody give me an equation where I have exactly twice as many blues as reds. What's the independent variable there? Red shirts. What's the dependent variable? Blue shirts. Well, what is it up there? What's my X? Red. And what is X predominantly? Independent. Yay? Nay? All right, let's get in this program here. So then that means that Y is dependent, correct? So if I have twice as many blues as I do reds, how do I show that in an equation? If I have one red shirt, how many blue shirts do I have? If I have two red shirts, how many blue shirts do I have? If I have 3 red shirts, how many blue shirts do I have? And how are you getting that? Doubling what? Doubling X. So then how would I write that as an equation then? How do I find Y? Close. Close. X equals 2Y. Means I take 2 times the blue shirts to get the red. What do you think? I said to you, Ashlyn, I take the number of red shirts and I times it by 2 to get the number of blue shirts. How do I write that in an equation? Okay, so if this was an equality, I find the number of blue shirts by taking the number of red shirts and timesing it by 2. Yes? Is that what that statement says? The committee expects to get twice as many blue shirts as red shirts. Yay? All right. But it says at least. At least that many. So how do I show that as an inequality then? Do I keep the equals to? What do I put in there? I need at least twice as many blues as reds.
Y is less than or equal to 2x?
Let's try it and see. Y is less than or equal to 2x.
No. It's gonna be the other way around.
What do you mean?
Like the side is greater than or equal to. Yeah.
All right. Here's what I want you to grasp today to begin with. If I have 1 red shirt, how many blue shirts do I have?
2.
I have 2. Could I have 3? Why not? It says all I have to do is have at least twice as many blues as reds. So, no. That can be 2 shirts. That could be 3 shirts. But then if I have a second red shirt, how many blue shirts do I have to have minimum? 4. But I could have 5. That's still twice as many, isn't it? That's still at least twice as many. So if I have 3 red shirts, what's the minimum number of blue shirts I can have? 6. Could I have 7? Yes. All right. So you understand this is going to be the part of this course, this module, this unit that is going to tie up your brain the most amount. You are going to have to figure this out. You are going to do multiple questions with that one statement right there. Twice as many juice as water. 1.5 times as much gas as oil. Those are types of questions that you're going to look at, and we need to know how do we get to them. So how did I get to this point here? Let's backtrack a bit. Think about a couple of the questions that I asked you to get to that point. What was the first question I said, and what was the statement that led you to this part? What was the first thing I said? Okay, we started there. And then from there, we did our restrictions. And then we figured out we needed x plus y to be less than or equal to 500, right? But then when we got stuck on this 2x part, what did I say to you? What should we find it out? How should we find it out first? As if it was what? An inequality or an equality?
Equality.
An equality, right? Let's figure that out. Let's see what the question's asking, and let's try something. So had you said, well, I'm going to put one blue shirt in. So if I have one blue shirt, that would mean I'd have to have half a red shirt. So that couldn't work that way, right? So then that means then I have to take the number of red shirts and I have to times it by 2 to get the number of blue shirts. So if I have one red shirt, that means I have 2 blue shirts. If I have 2 red shirts, I have 4 blue shirts, right? You need to be able to do that part. Now this part here is the part that I suspect didn't quite make sense at the moment. When I said, hey, I could actually have 3 blue shirts, and that still satisfies that statement. If I have 1 red shirt, I can have 3 blue shirts. That makes that true. Because when I put it in, 1 times 2 is what? 2. This is 3. Is 3 greater than 2? Yes. But the moment I had 4, or in the moment I had 2 red shirts, I had to have at least 4 blue shirts. I could have 5. That's what the inequality allows us. It gives us the flexibility to have a little more than what the equality does. The equality is very specific to 1 coordinate. The inequality is specific to multiple coordinates. All right, so now we got to graph this guy. Okay, first graph is x plus y is less than or equal to 500. Well, this coordinate here is 500 and 0. This coordinate here is 0 and 500. I just use my intercepts to graph that line. When I have large numbers like that, that's usually what I'll do. I'll use my intercepts. Okay, this guy, y is greater than 2x, is going to look something like this. Well, first, sorry, my bad. Okay, am I shading above or below this line?
Below.
Okay, it's less than or equal to it. So what do you think it should be? It should be below, but how do I check it? Put 0 and 0 in, right? So let's put 0 and 0 in. Is 0 less than 500? Yeah, so I'm talking about somewhere in here, right? Okay, but again, because it's whole numbers, what do I have to put in there? I have to put dots in there, right? Okay, now I got y equals 2x. That graph looks something like this. Okay, here's 0 and 0. I go up 1, up 2, right 1 to here, and that's what I have. Now what I need to do is I have to figure out where I'm shading. Now this is the money part of it. We already know I'm shading below this red line right here. I should have done this different. Hold on. Let's change colors here. All right, so I already know I have to shade below the red line. Now I got to figure out whether I'm above the green or below the green. And since it's at 0 and 0 already, I can't use 0 and 0. So I got to pick another coordinate. So let's pick 0 and 2. That's right here. 0 and 2. No, it's on the axis. Let's do this. Let's pick 1 and 5, let's say. So that should be about right there. 1 and 5. Let's check it. So I'm going to put this in. Y is 5, 2 times 1. Is 5 greater than or equal to 2? 5 greater than or equal to 2? Yeah. So this dot right here is in my shaded region. So let's show that.
How do you know what dot to judge by then?
I pick one. If it didn't work, then I would go below the line. Right?
But you said 1 and
I picked 1 and 5. I could have picked 10 and 0.
Okay.
I pick any one. I just need it. I need it to be somewhere in here or somewhere down here.
Right.
And then if it doesn't work, then I shade the other side of the line. There's my solution for this question so far. So any value in here is going to satisfy that. Now, we again are not here yet, but let's start talking about it. The vertices now become important parts of this whole thing. So these are my boundary lines right here. This red and this green now becoming blue. These are my boundary lines of my solution area. Okay? What we need to do is we need to find out what these coordinates are. So this one, of course, is 0 and 0 down here. This one is 0 and 500 right here. I need to find out what this intersection point is right there. So to do that, I would use Desmos, and I'd find my intersection point. That's what I would do. Now I could do it mathematically. I have x plus y is equal to 500. I can change that to y equals 2x. Substitute the 2x in for the y here. So I get x plus 2x equals 500. 3x equals 500. X equals, what does x equal? 500 divided by 3. $500 divided by 3.
166.6.
166.6 repeat.
Yeah.
Right? Okay. And subtract that from 500, and what do I get? Right, same thing. Okay, so this coordinate right here, those are called critical points. New to you today. Only thing new to you today is this. Critical points. We don't need it for 6.3, but we will for 6.4, 6.5. Those are called critical points. They are the vertices on your boundary lines. They are what we use for my optimization part of my problem, my objective. Okay? All right, now I did a whole bunch of work here that didn't need to be completed. It says, define the variables and restrictions. We did that. Write a system of linear inequalities that models the situation. There's my systems right there of linear inequalities. Graph the systems of linear inequalities. I just did that. Again, I would check it with Desmos. Suggest a combination of t-shirt sales that could be made. Well, a combination of t-shirt sales that could be made is any dot inside this boundary line. I could go 0 and 500. I could go 167 and 333. I can go any dot in there, and that would be a combination. Now, only one of those combinations is going to give me a minimum amount. That'd be 0, 0. I'd make no money. But only one of these combinations is going to give me a maximum amount. And what I would find out is probably that would be the maximum amount right there. If I sold 167 of the red and 333 of the blue, but that's all down the line. Okay? But this is where we're leading to. And again, what I'd like to see you do is do these 3 steps right here and then go to your graph as you work through in 6.3. Just because you're going to do that in 6.4 and in 6.5 is all problems. All right, and then we go through. So for our next class, I would like to see you get through the 7 questions on 6.3. All right. Again, you have Desmos. Put your phones into test mode right now if you haven't already done so. Any questions here from 6.1 or 6.2 that you want to ask about? I kind of went through 1, 2, 3, 4 yesterday on 3A, 4A. We're okay in here?
Seems like 6.3 and 6.2 are very alike.
Yes. Okay, we're good?